Okay, we're working on chapter 23 homework. Sorry, I didn't have that initially posted. Okay, so we have, let's see, 6 problems. So problem number 7, and this is convex mirrors and sign conventions. So problem number 7 is an object is placed 40 centimeters from a concave mirror of radius 20 centimeters. Find the location of the image. What is the magnification of the mirror? And is the image real or virtual? Is the image upright or inverted? So let's draw a picture. We don't necessarily need to draw a picture in this case, but we're going to do it anyway. So this is our primary axis, and I'm going to draw a mirror. And I've never tried this before, so I don't know how this is going to work. So let's try, see if I can rotate this thing. So it's kind of a little cheated because unfortunately it has that black line here, which I could make disappear by using a white pen. So, but I think you can ignore it for right now. Okay. So let's go back to the problem now. Object is placed 40 centimeters away, so this is the 40 centimeters. So let's draw this dimension in just to represent it, and it's to the center of the back of the mirror. So that's our object distance. So that's 20 centimeters or 40 centimeters. Okay, and then you have the radius, which is what they say, 20 centimeters. Okay, so the radius is here. So this is my object. The radius, let's just draw that. So if this were a circle, that would be the radius, which would be the same as there, circular path. And so R, and we use a capital R for that, is equal to 20 centimeters. So the question is, what's going to happen? Are we going to have a real, you don't need to use a ray diagram here, but I'm going to do it anyway just because I want to kind of prove something. So what happens? And so where is the focal point? Well, the focal point is actually half the distance. F is here. So if you take, well, we know the center is just going to bounce off and come back in. So if we took this and we went to the mirror and it bounces off the mirror, any lines that are going parallel are go through the focal point, like that. Okay, the other two that we can choose, and I'm just going to do one of them because if I do the other one, because this is not a perfect situation, is if I go to the center of the mirror, then I'm bouncing off at the same angle. So I'm going to try to make that the same angle. So those are my two rays of light. One is going in, bounces off through the focal point. The third one would be if we went straight here and hit the mirror. So I'm going to go ahead and do it. I'm just going to make it work. So what's going to happen is it's going to go through the radius, and actually it doesn't have to go through the radius, but yeah, I guess it does, because we want it to come here and then bounce off. So it kind of goes like that, and then it bounces off backwards. And so we get these 3 points. So our image is going to be this little doohickey thing here. So let me use black since that's what I did there. So my image is like that. So we can answer some questions. It's going to be smaller. Magnification is going to be less than 1. It's going to be negative because it's inverted. And it should be somewhere between the focal point and the radius. So it should be somewhere between 10 and 20 centimeters. So we don't have to go all the way back in the book. You know, we go to the summary, and we have the equation for mirrors. Actually, I don't see the mirror equation, but oh yeah, focal length is R/2. So we could use this equation, which is really just is the same for mirrors and lenses as long as you keep the sign conventions correct. So you could do that, or you can do 1 over the focal length. Focal length is R divided by 2. So what do we know? We know that P is 40 centimeters, and it's positive because it's on this side of the mirror, same size of focal point. Okay, and the radius is 20 centimeters. Okay, so we're trying to solve for Q. What's the object? So you're going to get 2 over R minus 1 over P. So I'm just subtracting this from both sides. And so we're going to plug that in. Rather than, we're going to solve for 1 over Q and then take the reciprocal instead of taking the reciprocal of this whole thing. Because it's not, if you take the reciprocal, it's not going to be R over 2 minus P. It's involves, you have to get a common denominator and et cetera, et cetera. So it's just easier if we just do it in this form. So we get 2 over 20 minus 1 over 40. And let's go ahead and find the common denominator just so we can do it. So the common denominator would be 40, so you multiply both the numerator and the denominator by 2, so you get 4 over 40 minus 1 over 40, which is 3 over 40. So Q is equal to 3 over 40. And then you take the reciprocal. So Q is equal to 40 centimeters divided by 3, which is going to be 13.3 centimeters, which is where we expect it to be. This is 10, this is 20, that's 40. So 13.3 looks perfect. Okay. So that's the position of our image, which is on the same side as our object. Now, as far as the magnification, let's just go back here. If we go again, look at the magnification of a mirror, and I don't really see it in the summary. So let's go back. Images formed by concave mirrors. So the magnification, this is equation 23.2, is just negative Q over P, which I guess is the same one as for mirrors, for lenses. So you have negative Q, 13.3 centimeters, divided by P, which is 40 centimeters. Okay, so that's going to be 1/3 actually, because this, if you multiply it by 3, you get 40, so it's negative 1/3. The centimeters cancel out. So what can we say? What's the answer to the question? The questions were, so let's go through it again. Find the location of the image. Check. Find what is the magnification of the mirror? The magnification is 1/3. So magnification, 1/3 means it's smaller, which we can see from the diagram. It's 1/3. And we can, because of the negative sign, this negative sign means that it's inverted, which means it's upside down. Is the image real? Yes, real. Why is it real? Because if you go to this, if you go to your handout, which I copied, and you go to, if you don't have that, you should have it. If you go to page 765, it says, okay, if P is positive and Q is positive, in the front it says that, let's see, where's real versus virtual? Well, because the image is located in the front, it's a real image. If it was in the back, then it would be a virtual image. So if Q is negative, then it would be a virtual image. Okay, so that's it. This is problem 16, chapter 23. So we have a convex mirror. So I'm going to use the same little thing I had used last time. So here's my mirror, except it's going to go the other direction. It's going that way. We'll draw a axis, or what do we call it? Yeah, primary axis, I think it's the word. And the focal length is going to be on this side. So this is focal. I'm going to put the focal length right here. So that's F. I think we showed the other day that, you know, with a convex mirror, the images are all virtual. Okay, so that's F. And what does it say F is equal to? F is equal to 8 centimeters. Okay, and the image is going to be somewhere over here. If the image is virtual, what is the object location for which the magnitude of the image distance is 1/3 of the mag? The image distance is 1/3 of the magnitude of the object distance. Okay, so, oops, that's not what I want to do. So let's draw my object like that. And again, we're going to the center of the mirror. So this distance to here, that's the object, okay, P. And then the Q is going to, let's read it again. If the image is virtual, what is the object location for which the magnitude of the image is 1/3 the magnitude? Okay, so if we have a virtual image, it's going to be over here. And what we're saying is that Q is equal to 1/3 P. So the virtual image is there. Because what's going to happen is the light rays are going to come in here. This one's going to bounce off, go through this focal point. So let's just kind of draw what's happening here. So we have our line. Light comes in here. It would normally, if it was a concave mirror, it would bounce through the focal point. Here it does go through the focal point like that, but the light really bounces off that direction. But we have the line that goes in the same direction through the focal point. So that's one thing that happens. What else happens? Well, if we have a ray of light that comes in here, it's going to bounce off like that, but what we do is we go straight in like that, and that the intersection of those two lines is going to give us the virtual image, which is right there. So it looks like, actually, if I did that correctly, it looks like it might be actually inside the focal point. So I'm going to move that to there. Okay, so now let's go to our sign convention, which is the big deal here. Because really the equation, the lens equation and the mirror equation is always the same. 1/P plus 1/Q is equal to 1/F. And the focal point, the focal length is always positive. So what we're going to have is we're going to have the image is virtual, so it's going to be negative. So if again you go to page 765, the object is in front, plus. The image is behind, which is negative. The focal length, oh actually the focal length is negative because it's in the back. So what we have is 1/, I'm just going to have plug the numbers in, and yes, okay. So we're actually solving for P. So P, we get 1/P plus Q, but Q is 1/3 P. And we put a negative sign here because it's behind. And we get negative 1/8. Okay, so P is positive. It's on this side. Q is on the other side. It's virtual, so it's negative, and its value is 1/3 P. The focal length is on the back side, so it's a negative. So dividing by 1/3 is like multiplying by 3. So we get 1/P and then minus 3/P is equal to 1/8. I'm going to leave the units off right now just so that when we get P, it'll be in the units of centimeters. Okay, we have a common denominator here, so we can just do that. We get negative 2/P is equal to 1/8. So we can cross multiply, and you would get negative 16 is equal to P. Did I do something wrong? Oh, yeah, this is negative. So it's negative. Negatives cancel out, so we can just make everything positive. And so we would get that P equals 16, right? 2 times 8 is 16. P times 1 is P, so P is 16 centimeters. And was that what they were asking us for? If the image is virtual, what is the object location for which the magnitude of the image distance is 1/3 the magnitude of the object distance? So P is 16 and Q is equal to 1/3 P. Well, actually it's going to be negative. So it's going to be 16 divided by 3, 16/3 centimeters. It's actually being negative because it's behind. How does that compare with 8 centimeters? Well, 16 divided by 3 is a little more than 5, so it actually does work out that our image distance is inside the focal length of the convex lens. Find the magnification of the image and state whether it is upright or inverted. Well, again, from the drawing, we know it's going to be vertical, and we know it's going to be smaller. But again, we can just use the equation that says the magnification is negative Q over P, negative Q, but Q is negative, so negative 16/3 divided by P, which is 16. And so what happens is you divide by 16, so you'll get positive 1/3. Okay, the negatives cancel out. This is the same as 16 divided by 1, which then you would take the reciprocal, which is 1/16, and the 16's cancel out, and you end up with 1/3. So it's 1/3 the size of the original, which is what it looks like, and it's positive, so it's upright. So I think we did that one right. Okay, problem 24 is a swimming pool problem. We talked about that the other day. So let me draw a swimming pool. So we're just going to draw a rectangle. So here's a swimming pool. And so it says the top of the swimming pool is at ground level. If the pool is 2 meters deep, how far below ground level does the bottom of the pool appear to be located when the pool is completely filled with water? When the pool is filled halfway with water. So how far below ground level does the bottom pool? Okay, so the first case is where it's full. And if you go to, I think we have a drawing. We talked about it the other day, and I can't remember whether we actually, if there's actually something in the book. Yeah, it's flat reflecting surfaces. So this is figure 23.16. So what it says is if you have an object here on the floor at the bottom of the pool and you have light coming up here, because the index of refraction of this is greater than air, it bends away. So you get these light rays that go like this, and this one bends away, and then you get one that goes like that, and it bends the other direction away from the normal. So this is all Snell's law, and so then if you extend these in, the person on the surface sees these rays of light, which then do something like this. I did this all right, which is not exactly right, but what you see is that the floor, the bottom of the pool appears to be closer than it really is. So if we can figure out what this distance is, then that's going to be what we think the depth of the pool is from the ground level. Now when we have half the pool, then we're going to have the actual physical distance of half the pool and then the reduced distance for the second part. So the equations, if you go to page 770, it says for that situation that the image is located negative in 2 over N1 times P. So P is the distance the object is. The object is the bottom of the pool in this case. So P is equal to 2 meters. And since we're dealing with air and water, N1 and N1 is the, if you look at the figure, N1 is the index of refraction of the material, which I guess it said water. Maybe it's a pool. So I actually have to go back to chapter 22 and look up the index of refraction of water, which I think is 1.33, but if we used it enough, we should be able to know what it is. But refraction water 1.333, so 1.333, and N2 is air, which we just round off to 1.0. And what this should be shorter, so Q is equal to, if this works out right, Q should be less than P, which it is, and P is 2 meters. And so we get negative, which means it's a virtual image, which means that it's not on the other side of the boundary. So 1 divided by 1.333 times 2 is 1.5. So the pool looks 1.5 meters deep instead of 2 meters deep. Now, what happens to the, if it's half full? Well, if it's half full, what's going to happen is P is 1 meter. So you get Q is equal to 1.0 divided by 1.333 times 1 meter, which is, that's 0.75, because that's what that is. So it's minus 0.75 meters. But you've got also the distance from halfway the pool to the top. So the total distance in that scenario is going to be the actual 1 meter that's not filled plus the 0.75 meters that the pool, the water makes it look shorter, so you get 1.75 meters. So 1.75 meters. So the pool looks 1.75 meters deep when it's half full. It looks 1.5 meters deep when it's entirely full. Okay, problem 29 is just the lens, using the Lensmaker equation. So let's see what that is. It's on your handout. So it is, we have to go back into the, I looked at the summary thing and, okay, so this is equation 2312. 1 over the focal length of the lens is n minus 1, where n is the index of refraction of the glass, minus 1 over R2, 1 minus R2. And let's see, what does it say? What is R1 and R2? Focal length of lens in air related to the curvature of its front and back surfaces. So R1 is the radius of the front, so R1 is the front, and R2 is the back. So in our particular case, so this is just a plug in the chug kind of problem. So an N is 1.5. And so the front is 1.5, well, there we go, 2 centimeters, 2.0 centimeters. And the radius of the front is the inner, the back, which is 2.5 centimeters. Okay, so what do we get? We get 1 over F is equal to 1.5 minus 1 times 1 over R1, which is 2.0, minus 1 over 2.5. Of course, the second one has to be, this radius has to be greater than that radius, or you would get a negative number, which wouldn't be good. Okay, so we get 1.5 minus 1 minus 0.5 times 1 divided by 2 minus 1 divided by 2.5, and we get 0.05. And then we just take the reciprocal. So f, you could just say it's 0.5 to the minus 1 power. You could say it's 1 over 0.5, however you want to do it. So since I have 0.05 in my calculator already, I'm just going to raise it to the negative 1 power, and I get 20. So I get 20.0 centimeters. Okay, because the original things were 7 centimeters. That was easy. Okay, we were down to 2 more problems. 31. It's a black problem, so it's another easy one. A converging lens has a focal length of 10 centimeters. Locate the images for object distances. Yeah, I think we did that in the class, didn't we? I don't know. Not sure if we did or not. I thought I picked ones that were not in the book, so if we did, then you're lucky. But so again, I'm going to draw this, and I'm going to draw it as this other kind of lens here, this particular shape, just because I can make it thin, and I can rotate it around, and it looks kind of like a lens. And I think it would be this way. Yeah, there we go. Okay, so there's my lens. It's a convex lens, and it's a converging lens. Okay, so the focal length is 10 centimeters, so I'm going to put my focal length. We've got 2 sides, so my focal length is 10. Centimeters. Okay, locate the image for object distances of 20 centimeters, 10 centimeters. Yeah, we did that. Probably did it in class, so we'll do it again just in case you forgot. So we have 20 centimeters, 10 centimeters, and 5 centimeters. And probably the best thing to do is just to do all these separately. So what I'm going to do is I'm going to go over here, and I'm going to, it's almost, oh, look at that. You can actually bounce the arrows off of there. Interesting, didn't know that. So what I'm going to do is I'm going to copy this. And, okay, edit, copy. Click on there so it takes it off. Okay, edit, paste. Huh, okay, I thought I could do that, but I guess not. Edit, copy. Okay, then I'm going to paste it. Oh, that's not what I wanted to do. That's okay. Still hasn't copied it. Let's see. Let's try again. Maybe it wants me to. Let me move this out of the way. I'm just going to group them all together. So we'll group them as a group. Now I'll copy them. Copy, paste. Okay, so that's one. Now let me bring one of my arrows over here. So we're going to do that one there. We'll have the third page. So let's paste that. There it is. And then we'll bring my arrow over. I guess I really don't need to drag this thing all the way over there, but what happened to my, oh, there's a page in between. So let me delete that. Okay, there it is. Now I can bring this over here and I can put it right there halfway. Okay, so those are the 3 cases, and this one's 20 centimeters, which places it about right there. So I'm going to do the ray diagrams. Again, we could just use the equation, but I want to explain how the image is formed. So you go through here, through the center of the image, and then that line that's parallel goes through the focal point. Okay, so that's one thing. The second ray goes through the center and it just goes straight. So you get that point. And the third ray goes through this focal point, intersects there, and then goes out parallel. So that's where the image is located. And based on looking at it, it looks like it's going to be the same size, same distance as the original image. So the original object. It's going to be inverted. It's like the magnifications should be about the same. So that's the first one. Let's do the second one. So here, so we'll do that. And this may not work out perfect because I didn't exactly place the focal length. So this one goes through there. It goes through the focal point. This one goes straight through the middle. Okay. Okay. And this one goes through the focal point, which is right there, which goes there. So actually, these are all kind of going off in weird directions. For some reason, I thought they all should go through the same point, or should go to the focal point. Am I doing something wrong here? I'll come back to that one. Let's see. Okay, this one. Okay, so we have this go over here, that goes to there, it goes through the focal point like that, and then we have this going straight through the middle of the mirror like that, and then we have this one actually goes through the focal point, so this would go up there, and if the lens were big enough, it would go out parallel like that. Okay, so if I drew the lens wide enough, this, which goes through the focal point, would go up to this intersection, go up there, and so what you have is all these virtual lines that come back. So they diverge, so all the other ones go like this, they're just extended back through the mirror, and they are located there. So our image is going to be right at that point. It's going to be bigger, it's going to be upright, and it's going to be virtual because it's on the same side as the original object. This is a real image. It's inverted because if you put a screen there, it would work. So the lens equation says 1 over P plus 1 over Q is equal to 1 over F. F is equal to 10 centimeters. And let's go to the sign convention situation here. So if I can find my thing with sign conventions, it's on page 775. So the image should be in back. So Q is positive, should end up being positive. P is positive, and P in this case is 20 centimeters. So we can solve for Q. 1 over Q is equal to 1 over F minus 1 over P. So we get 1 over 10 minus 1 over 20, which is equal to, well, that's 2 over 20 minus 1 over 20, which is 1 over 20. So 1 over Q is equal to 1 over 20, therefore Q is equal to 20 centimeters. Okay, so since it's positive, it's in the back of the lens, so that means it's a real image. And then if we do the magnification, let me just add a page here. So the magnification is negative Q over P. So we have negative Q, which is 20 centimeters. That Q is positive. P is 20 centimeters positive. So we get negative 1. So the size is the same, but it's inverted, which is what we said. Okay, the second case is we have 1 over P plus 1 over Q is equal to 1 over F. So again, if we solve for the distance for the image, it's going to be 1 over P 1 over f minus 1 over p. Okay, so what I do is I just subtract 1 over p from both sides. Let me add a page. Okay, so what do we have? We have p is equal to 10 centimeters. We have f is equal to 10 centimeters. So we get 1 over q is 1 over 10 minus 1 over 10, which equals 0. So 1 over q equals 0, or q is equal to infinity. And so the image does not exist. Okay, third case is this one. So same equation, 1 over p plus 1 over q is equal to 1 over f. Again, solve for 1 over q. It's 1 over f minus 1 over p. So f is 10 centimeters, and p is 5 centimeters. So we get 1/10 minus 2/10. 1/5 equals 2/10. So we get negative 1/10. So q, 1 over q is negative 1/10. Therefore, q is equal to negative 10 centimeters. Which is the focal point on that side. So that's kind of what we say. We didn't get exactly right, but so q is negative 10 centimeters. Positive q is on the right-hand side, negative q is on the left-hand side. So it's over here. And our magnification is negative q over p. So we get negative and negative 10 centimeters. P was equal to positive 5 centimeters. So the negatives cancel out, and 10 divided by 5 is 2. So the virtual image is twice as big as the actual image. It's positive, so it's upright. So it's upright, magnified, it's virtual, and it's located 10 centimeters on the same side as the object. So this is a magnifying glass situation.